This video is over lesson 83, probability of dependent events, and it is for my pre-algebra classes. So ladies and before we get to dependent events, first we're going to handle independent events, and these are the ones that you're actually most used to working with because typically we just have found probabilities of one event, one action, but now we're moving up to looking at what happens when we have multiple actions. So we start with independent. Remember that the prefix in means not. So these are not dependent, or they do not depend on each other. And so they are in events where the outcome of one event has no effect on the likelihood, the probability of the outcomes of the others. So whatever happens in one of them has no effect on the probability of the other. That's an independent event. Okay, they do not depend on each other. So examples of this would be if I were to take look at the probability of pulling a card from a deck of cards, and then I put it back in, shuffle it back up, and pull another card. Okay, so I put the card back, so the probability of pulling out, another card is just the same as it was before. Another example of independent events are rolling dice. So you could roll a die and then roll it again. It doesn't matter what you got the first time. It does not change the probabilities of what you'll get the second time. You could take a look at flipping a coin. If I flip a coin and I get heads, it does not affect the probability of getting heads or tails the next time. Likewise, another one that comes up often is pulling marbles from a bag. So if I have a bunch of different colored marbles in a bag, if I pull one of them out and then I put it back in, shake them up a little bit, pull one out, because I put the marble back, the probabilities remain the same. So those are all independent events. And so for independent events, we have a formula for finding their combined probability. So remember, we start with a capital P, and then in parentheses, we write what we're finding the probability of. So this literally reads probability of, and then whatever's inside here. So probability of A and B. So A is one action, one event. B is the other action or the other event. Now, one thing we need to understand here is while we often use the word and, there really is an order that is implied. So in some ways, the and is almost really a then. So it's really almost more the probability of A, then B. So probability of getting whatever this is talking about, then getting whatever this is talking about. Now, independent events are nice because their probabilities do not affect each other. Their outcomes do not affect the other events' probabilities. We can just split this apart. And so this really just becomes the probability of A times the probability of B. So independent events are real nice in this regard. So by way of an example, let's say we want to find the probability of rolling. So we're talking about a die, a number cube. I want to know the probability of a 5 and a 3. So let's say I'm playing a board game with my family, and I realize that on my next turn, if I can just roll a 5 with the die, and then I roll it again, and if I get a 3, if I get that combination, I will win the game. So what is the probability I'm winning the game on my next turn? Well, getting a 5 has no effect on whether or not I get a 3, on how likely it is to get a 3. So I can split this up into the probability of getting that 5 times the probability of getting that 3. Well, 5 is just one option out of 6. So the probability of getting a 5 is 1/6. Likewise, 3 is only one option out of 6 possible. So it also has a probability of 1/6, which means the probability then that I'm going to win the game on my next turn is 1/36. So it's possible. It's not likely. It'd probably be a big upset if I actually were to win the game on my next turn then. Another quick example, what is the probability of flipping a coin twice and getting heads both times? So again, whether I get heads or tails the first time has no effect on the probability of the second flip. So this is independent, and we can split it up to the probability of heads times the probability of getting heads a second time. Well, the probability of getting heads is 1/2 for both of these, which means that the probability of getting double heads is 1/4. So those are independent events. Now we're going to move on to the topic that the title has been telling us about. And we're going to talk about dependent events. So dependent events are events where the outcome of one event, so remember the prefix in meant not or no. So this time there's no in, so there's no no. Events where the outcome of one event has an effect on the likelihood or the probability of the outcomes of the other. So independent, they don't depend on each other. They don't affect each other's probability. Dependent events, one of them does affect the other. So a good example of this would be going back to our deck of cards. If I pull a card out of a deck of cards, there are 52 cards to begin with. But if I pulled a card, now there's only 51 left. So if I don't put that back, the probabilities will be different for my second card that I pull. Likewise, a bag of marbles. If I've got a bunch of colored marbles in my bag and I pull a marble out, well, if I don't put that back in, then I don't have the same number of marbles that I had to start with. That will change the probabilities. So those would be both examples of dependent events. So you'll get things like that where we have decks of cards, we'll have names that maybe we put in a hat, bag full of marbles, and these things are independent if we replace them. So we say with replacement, they are independent, but then without replacement, they become dependent. And the formula for dependent events actually changes a little bit. So the probability of A and B, and once again, when we see and here, we should really be thinking then. So it's implied by the order we put it in there that the A event happens first and the B event is happening second. And so the formula here is still going to be the probability of A. Since that is the first event, its probability doesn't change. Nothing's happened to change it. But then what we say over here is we call the next one the probability of B, but we say given A. The probability of B given A. And this right here is what's called a conditional probability. It's a conditional probability. So we're finding the probability of B under the condition that we assume that A has already happened. So again, we're finding the probability of B under the condition that we assume that A has already happened. And we'll see what this looks like here right now. So let's say that I want to know the probability in a deck of cards of pulling a king, then an ace. So what's the probability of pulling a king, then an ace? So this will split up into, and we're going to say without replacement so that it's dependent. So the probability of pulling my king, that's the first thing, so that probability is not going to change. And then we're going to multiply that by the probability of pulling an ace, given that we've already pulled our king out. Well, if you know your deck of cards, you have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you can, in your mind, imagine that the ace is like a 1, then you count up to 10. And then after 10, we've got a jack, a queen, and a king. So that's a total of 13 cards in each of what we call a suit. And the suits are the symbols that you see on the cards. And those include hearts, diamonds, spades, and clubs. So we got 4 suits. So a deck of cards is 4 groups of 13. That's 52 cards total. So here's the thing. For the king, each suit is identical as far as what numbers and what face cards it has. So there's 1 king out of 13 cards in the suit. And that's going to be true for every suit. So you're going to have 4 kings over 4 times 13 total cards. So really, it's just 1/13. The probability of pulling a king is 1/13. It's really 4 over 52, but that's 1/13. Now, the probability of A given K. Well, there are 52 cards to begin with, but I've pulled a king out, which means that now there's only 51 cards left. Since the 1 card we're assuming we pulled out was a king, that means all 4 aces should still be in there. That's my conditional probability. So under the condition that a king has been pulled, now there are only 51 total cards left, but 4 of them are aces. So if we go ahead and multiply that together, 1 times 4 is nice and easy. And then down here, 13 times 51, if you grab your calculator real quick, 13 times 51 should come out to be 663. Now, if you're not super familiar with decks of cards, that might have been a little hard for you to follow. So we're going to do another one now, or another several actually, where we're going to go to this idea of having a bag of marbles. So if I have a bag of marbles, we're going to make a bag of marbles here. So that's going to be the fluff at the top of my bag. It's got kind of a fluffy opening. And then here's my bag itself. And inside my bag, we're going to say there are 3 red marbles. I'm going to say there are 2 blue marbles, and then finally we're going to say there's 1 white marble. And I'm not going to draw them all out, and you may or may not have the right colors for that, so we're not going to worry about that, but just know that that's what we're saying is in the bag. So if I want to find the probability, so R will stand for red, so RR would stand for pulling 2 reds. And again, we're assuming without replacement. So if I want to find the probability of pulling 2 reds, then this is going to equal the probability of pulling my first red times the probability of pulling my second red, given I've already pulled one. So the probability of pulling the first red, well, there are 3 reds out of 6 total. So if there are 3 reds out of 6 total, well, 3 is 6, that's 1/2. We can do a quick little reducing there. So the probability of pulling a red the first time is 1/2. But once I've pulled a red out of the bag, now I've only got 2 reds left. So when I go to find my next probability, my conditional probability, there are only going to be 2 reds left out of 5 total now. If I come over here to my dry erase board for a quick second, so just to kind of model that. So the first probability I had 3 out of 6. And then for my second probability, one of my reds is gone. So the second probability I got, because there are 2 reds left out of now 5 total. That's where we got those numbers from. Okay. So now I've got a fraction times a fraction. We can do a little reducing before multiplying. So 2 and 2 will both turn into 1s. And so this is a 1/5 probability. So if I pull 2 marbles out of my bag, about 1/5 of the time I should get double reds. So now I'm curious, what is the probability then that I pull let's see here. I want to know what's the probability that I pull double blues. So what's the probability of double blues? So it's going to be the probability of the first blue is just going to be the same. But then I'm going to have the probability of pulling a blue given that we've already pulled a blue. So for this one, the probability of pulling a blue, there's 2 of them out of this 6 to begin with. Or if we look over here, right? 2 out of the 6 total. And then the probability of pulling a blue, given that we've already pulled a blue. So my conditional probability, we've already pulled a blue. Now I'll only have 1 left out of 5 total. And of course, 2/6 reduces down to 1/3. So then I'm going to have here 1/3 times 1/5. So about 1/15 of the time, I should get double blues. About 1/15 of the time, I should get double blues. Well, as long as we're talking about doubles, let's go ahead and continue with our doubles and say what is the probability of getting double whites. So then this will be the probability of pulling a white, and then the probability of pulling a white given that we've already pulled a white. So the probability of pulling a white, there's only 1 white out of 6 total. So that's 1/6. For my second probability, if I come back over here and reset my bag, so remember the first probability was 1/6. There's 1 white marble out of 6 total. Now the second probability is the probability of pulling a white given that we have already pulled a white. Well, if we've already pulled a white, there are no white marbles left. That means it would be impossible to pull a second one. And remember that when something is impossible, it has a probability of 0. So my conditional probability here, there won't be any white marbles left over to pull, so it's 0. And of course, 0 times anything is 0. So it would be impossible to pull double whites. Now, a quick note about this. Really, for this one, we have a special case, because if you look at the bag, you can see right from the beginning that it is impossible to pull 2 white marbles. So actually, you could have just gone straight to 0 and just declared that it is impossible to pull 2 white marbles from a bag that only has 1 white marble. All right, we're going to mix things up a little bit now and get away from our doubles. I want to know, next up, what is the probability of pulling a red marble followed by a white marble? So without replacement, that's going to be the probability of pulling the red first, and then times the probability of pulling a white, given that we've already pulled a red. So the first one's easy, the red. We have 3 red marbles out of 6 total. Well, 3 out of 6 is 1/2. The second probability, so remember the conditional probability here, we got to actually think about what's going on. So we're trying to find the probability of pulling a white marble. So there's only going to be 1 of them, but assuming that we've already pulled a red. So out of 5. So the conditional probability there is 1/5. Meaning that about 1/10 of the time, you will pull a red marble followed by a white marble. About 1/10 of the time. Well, ladies and gentlemen, we can extend our dependent probabilities here. And I can actually find what's the probability. Let's get real patriotic here. What's the probability of pulling 3 marbles, starting with a red, followed by a white, finishing off with a blue? So we get real patriotic. So this then, just extending our formula, would be the probability of pulling the first one, red. And then our conditional probability is going to be the probability of pulling a white, given that we've already pulled a red. So far, this actually matches what we just did up there. So we know the first one's going to be 1/2. We know the second one's going to be 1/5. And then times the third thing here is going to be the probability of pulling that blue, only this one is given that the first two have already happened. So given that a red and a white have already been pulled. So again, we said we know the probability of pulling a red is 1/2. We know the probability of pulling a white, given that a red is already gone, is 1/5. And so now it's down to the last one. So if I start that over, remember the probability of pulling a red here is 1/2. Then assuming that I've pulled a red already, the probability of pulling a white is 1/5. And then the last probability is going to assume that I've pulled a red and a white. And so I'm looking for the blues. So I have 2 blues out of 4 total now. In other words, the last probability actually is another 1/2 if we reduce it. So if a red is gone and a white is gone, then pulling a blue has a 1/2 probability. Multiply these all together. 1/2 times 1/5 times 1/2. If you pull 3 marbles from the bag, about 1/20th of the time you're going to get something real patriotic there, red, white, and blue. And just to finish it off, last one, I want to find what's the probability, since I have 3 reds in there and we're talking about pulling 3 marbles, what's the probability of pulling 3 reds? Now obviously, what's the probability of pulling 3 blues? 0, it's impossible. What's the probability of pulling 3 whites? 0, it's impossible. But we can pull 3 reds. So if I pull 3 reds, it's going to be a probability of just pulling the first one times the probability of pulling the second one, given that we've already pulled one. And then that's going to be times the probability of pulling the third red marble, given that we've already pulled 2 red ones. So over here, if I reset my bag here, we know the probability of pulling that first red one is 3 out of 6, or 1/2. So I've pulled it out, it's gone now. The probability of pulling the second one, given that one of them's already gone, now there's 2 out of 5 total. And then for the third one, we've already pulled 2. So what's the probability of pulling that third one? Well, there'll only be 1 red one left out of 4 total. So 1/2 times 2/5 times 1/4. 1/2 times 2/5 times 1/4. A little reducing before multiplying, the 2's will cancel and become 1's. And then we find out up top, I got a 1's all on top, and 1 times 5 times 4 is 20. So actually it turns out you are just as likely to get a red, white, and blue as you are to pull 3 reds. And that, ladies and gentlemen, is the end of our lesson.